This is Math 105, section 4.1. Now we're going to talk about a class of functions called exponential functions. Okay, exponential functions have the variable in the exponent. Okay, so those are exponential functions. So for example, we could have our base is going to be a constant. Okay, so here we have our base is 2 and our exponent is x. Okay, so f of x equals 2 to the x is an exponential function. This grows really fast if you think about x being positive values, maybe positive integers. You can see when x is 3, so this is base 2, right? When x is 3, we're multiplying 2 3 times. When x is 10, we're multiplying 2 10 times. So this, when x is 3, we have 8. When x is 10, we have 10 24. So this grows really fast. And when x is 30, we have 2 to the 30th power, which is 1,073,000,000, etc. Okay. If we look at x squared and look at 30, 30 squared is just 900. So this thing, at first it looks like x squared, but it grows super fast once you get to larger values of x. Okay. So the key is here that when the variable is in the exponent, okay, for exponential functions, which is true, even a small change in the variable can cause a dramatic change in the y value, in the value of the function. Okay, so a small change in x can give you an enormous change in y. Okay, so now let's talk about exponential functions in general. So we're going to use this exponential expression a to the x, where x is any real number. So x is our variable. Okay, we're going to define a of x for a greater than 0. Okay, and x a rational number. Okay. We already defined that. Now we're going to look at irrational powers. Okay. So what is, remember we said like 8 to the 2/3 is just, we can say it's 8 squared to the 1/3, right? In other words, we're taking a cube root and squaring it, right? Or vice versa, we're squaring it and then taking the cube root. Well, now we're going to look at irrational powers of x, okay? Like 5 to the square root of 3, or 2 to the pi power, 5 to the square root of 3 power, 2 to the pi power. Okay, so we're actually going to, once we get into this territory, when x is irrational, we approximate x by rational numbers, okay? So, for example, we could say, square root of 3 is approximately 1.73205, and then as we go out more decimal places with our exponent, we get closer and closer to that a to the square root of 3. Okay, so this is, as we use closer and numbers that are closer and closer to the square root of 3, we're going to get closer and closer to our approximation there. So let's say we use 1.732 as our approximation for square root of 3. Then we can say, using a calculator, we can say 5 to the square root of 3 is approximately equal to 5 to the 1.732 power, okay, which is 16.24. Okay. Okay, when the exponents are real numbers, laws of exponents are still true. Okay, so they apply. So for exponential functions, in our case, we'll look at the exponential function with base a. Remember, a is a number greater than 0. Okay. And we're going to say a is not equal to 1 also. Okay, so it's a non-zero. Sorry, it's a positive number that's not equal to 1. Okay, and this is what our function will look like. F of x equals a to the x. Okay. Okay, we say a is not equal to 1 because when you take 1 to the x, you always get 1. It doesn't change. It's just a constant function. So we're not going to really focus on that one. It's not very interesting. So that's why we say a is not equal to 1 for our base. But our base will be a constant that's positive and not equal to 1. Okay, and remember, our exponent is the variable x. Okay, so here's an exponential function with base of 2. Here's one with base of 3. Here's one with base of 10. Okay, so a quick example. Let's say we have our base of 3. So f of x equals 3 to the x, and we're looking at f of 2. So we're going to look at 3 squared. F of 2 would be 3 squared, which is 9. Okay. Let's look at some other ones. So f of minus 2/3 would be 3 to the minus 2/3, which is 1 over 3 to the plus 2/3. And using a calculator, we can enter 3 to the minus 2/3 in parentheses, minus 2 divided by 3, enter, and that we would get 0.4807. Okay. 3 to the pi power is about 31.544. 3 to the square root of 2 power is 4.7288 approximately. Okay, now let's look at the graphs of our exponential functions. So let's start with 3 to the x. So we'll look at f of x equals 3 to the x, where our base is 3. And then we'll look at a function where we're looking at 1/3 to the x. So notice our a is 3 here, and here our a is 1/3, which is a reciprocal of 3, right? Still positive, right? But it's a fraction. Okay, so if we take 3 to the x, we're going to get this red graph right here. Okay. Now notice it always goes through 0, 1. And the reason is because when your x is 0, you're taking 3 to the 0 power, or 1/3 to the 0 power, and anything to the 0 power is always 1. So your exponential function will always cross 0, 1 if there's no other number in front of it, if it's just 3 to the x or 1/3 to the x. Okay, so here are the values we got for x equals -3, -2, -1, 0, 1, 2, 3. For 3 to the x, 3 to the 0 is 1. Okay, 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. But when we go to negative powers, so 3 to the -1 is 1/3. Okay, 3 to the -2 is 1/9, and 3 to the -3 is 1/27. Okay, looking at the red graph again, so it grows really fast when x is positive, okay, but it goes down towards 0, towards y equals 0 when x is negative, and it gets small. So we're getting fractional values. It never hits 0. Notice this function is never negative. It's always positive. Okay? So our domain is all reals, okay? And our range is y is greater than 0. So let's write that out for these. In fact, that's true for both of these. So for both of these functions, domain x can be any real number, and range is y is positive. Can't be negative or 0. Okay? And that's true for all exponential functions. Okay? That have that a being positive. Okay, now getting to the 1/3 of the x. Notice the opposite happens. When we take 1/3 to the 0, we get 1, of course. 1/3 of the 1 is 1/3. 1/3 squared is 1/9, and 1/3 cubed is 1/27. Okay, and then we take 1/3 to the -1. We're taking 3 to the +1. Okay, so that's a 3. 1/3 to the -2 is 3 to the +2, so that's a 9. And then 1/3 to the -3 is 3 to the +3, which is 27. Notice our values are all positive again. So when we have 1/3 of the x, we've got this blue function. And that's also an exponential function, but that's when our base is a fraction, is less than 1. Okay? And notice these are related. That this is just a reflection, the blue is just a reflection of the red across the y. So really what this function is, this y equals y to the 1/3 x, is this. Think about, we're changing our x to the opposite sign, right? Okay. This is the same thing as saying y equals 3 to the -x, right? Which is the same thing as 1/3 to the +x, okay? So notice that you're changing the sign of x, you reflect across the y-axis, right? And that's what we're doing there, okay? So we're not going to generally look at exponential functions with a negative in the x like that until we get to exponential decay. So we're going to use a base of 1/3 instead of 3 to the -x. Okay, but recognize that that's what happens. That 3 to the -x is 1/3 to the +x. Okay, all right, and we can see that these functions reflect across the y-axis. And algebraically, we can see that 1/3 of the x equals 1 to the x over 3 to the x, which is 1 to the x is 1, and 3 to the x is a denominator, which is 3 to the -x. Okay, so that's f of -x. So we could have obtained the graph of g from the graph of f by reflecting in the y-axis. Okay, now let's look at a whole class of exponential functions, and we're going to start with the red over here. Okay, so this red is 2 to the x. Okay, and notice they all go through 0, 1. Okay. This is 2 to the x. The 3 to the x that we looked at before is the black here. Okay, so we're going to relate 2 to the x to 3 to the x. Okay, and then 5 to the x we can see gets even steeper. Okay, it gets closer to the x-axis as we go down this way. As our x is negative, and then it goes up faster. And then 10 to the x is the purple. So let's focus on this part first, where we have 2 to the x, 3 to the x, 5 to the x, and 10 to the x. And you can see that pattern. It always goes through 0, 1, and it grows faster and faster as you get to higher bases. Okay. Now let's reflect across. The red goes with the red. So the 2 to the x and the half to the x are basically a function just reflected across the y-axis. Okay, remember this is the same as 2 to the minus x, or 1 over 2 to the x, right? Okay. So the red reflects the red across the y, 2 to the x and 1/2 to the x. The black reflects the green. Okay, now we're doing black to green. So 3 to the x and 1/3 to the x. Okay, and then the blue reflects the blue. Okay, so 5 to the x and 1/5 to the x. And then the purple reflects the yellow, 10 to the x and 1/10 to the x. So you can see those reflections, but so these are all the fractional powers, okay, sorry, the fractional bases, and these are the bases that are greater than 1. But we can see how they're related. You know, 2 to the x and 1/2 to the x are related. 3 to the x and 1/3 to the x are related. 5 to the x and 1/5 to the x are related, and 10 to the x and 1/10 to the x are related. Okay? They're just reflections across the y-axis. Okay, so it's important to note that all of these graphs pass through the point 0, 1, because a to the 0 equals 1 for any a that's not equal to 0. Okay, so we have two kinds of exponential functions. Okay, generally, the first type we looked at was a is greater than 1, which means the function increases rapidly, and those are the ones that go up high to the right. Okay, and then we have the case where a is a fraction. Okay, a is between 0 and 1, and the exponential function decreases rapidly. It just does the opposite. Remember, it's reflected across the x-axis. So those are the ones that go down, that go down really fast, and then they go down slowly after they go through 0, 1. Okay, so here's our class of functions again, right? Remember, we have 2 to the x, 3 to the x, 5 to the x, and 10 to the x. And then across the y-axis, we have 1/2 to the x, 1/3 to the x, 1/5 to the x, and 1/10 to the x. Okay. Some things to note, though. We have a horizontal asymptote for all these, right? And that's the x-axis. Okay. And that's because when a is greater than 1, we have a to the x approaches 0 as x approaches minus infinity, and that's happening over here, right, as x approaches minus infinity. We're looking at these now, okay, the ones with 2, 3, 5, and 10 as our base, right? As x approaches minus infinity, going to the left, what happens? A to the x, our y, approaches 0. See, it's going down to 0, okay? And then just the opposite happens when a is a fraction. So when a is a fraction between 0 and 1, okay, we have a to the x approaches 0 as x approaches positive infinity. So that's on this side. Now we're looking at these, you know, the 1/2, the 1/3, and the 1/5, and the 1/10 to the x. See, as x approaches positive infinity, going to the right, our y is approaching 0. So all of these functions, they don't have a vertical asymptote, but they have a horizontal asymptote of the x-axis, which is just y equals 0, right? So, okay, we already said that a to the x is greater than 0. Okay, so the function f of x equals a to the x has domain all the reals, and the range is 0 to infinity, greater than 0. Okay, so let's just summarize. Let's do a follow. Okay, so the graphs of exponential functions. The exponential function f of x equals a to the x. I'll put it larger there. A is greater than 0, a is not equal to 1. Okay, has domain all reals and range 0 to infinity, not including 0. Okay, the line y equals 0, the x-axis, is a horizontal asymptote of the function. Okay, and the graph has one of the following shapes. Okay, so this is when a is greater than 1. Okay, it goes up really fast, and when a is between 0 and 1, a fraction, it goes down really fast. But notice it always goes through 0, 1, okay? Okay, now let's look at some graphs we're given, and we want to figure out what the function is. Okay, now notice both of these go through, see that's 1 there. Both of these go through 0, 1. Here's 1 here. So that we know they're exponential functions, right? Because this one's going up really fast, one's going down really fast. So let's figure out what this is. Okay, so think about this. 2 to the 2 and 25, right? 2 is our a, okay? And now remember so 2 is our x, right? And we're looking at f of x equals a to the x, right? So we can say a to the 2 equals 25, right? So that means our a must be 5, right? Okay, so this would actually be f of x equals 5 to the x. Okay. Let's switch colors. Now we know over here on the right that it is an exponential function, but it's going down really fast. So our number will be a fraction. Okay. Well, we know we're going to start with f of x equals a to the x, just like we did before, right? Or g to the x, whatever. Okay. Equals a to the x, but we know a is going to be a fraction. Okay. Now let's plug in. So x is 3, so we have a cubed equals 1/8, right? Because remember, our y is 1/8 and our x is 3. Okay. And how do we get 1/8 when we cube it? Well, if we take 1/2 and cube it, you get 1/8, right? Okay. There's a 3 there. Okay. So this one is going to be, let's call it g of x, even though I used f up there, is 1/2 to the x. Okay. Okay, so just to summarize, looking at a, here's our graph again. A squared equals 25, okay, because x is 2 and y is 25, so we can say that our base is 5. Okay, so f of x equals 5 to the x, so that's this one. Okay, here we know our base is going to be a fraction because it's going down, right? So it's going to be less than 1. And we have a cubed equals 1/8, right? Because here's our 3 for x and our 1/8 for y. Okay, so we put the x here and then the y is going to be the 1/8, right? So 1/2 cubed is 1/8. So this is our function. F of x equals 1/2 to the x for the second one. Okay, now for this next example, we're going to compare 2 to the x, which is our exponential function, and our basic quadratic, x squared. Now, that's not an exponential function, that's our quadratic, right? Okay. So we're going to look at different viewing windows, just looking, using a graphing application. So this will be our 0.3 by 0.8, 0.6 by 0.25, and 0.20 by 0.1000 for our x range, our y range. X range, y range, x range, y range. So we'll just look at this, kind of to compare the two. So when we have 0 to 3 for x and 0 to 8 for y, you can see that x squared grows faster at first, okay, the blue, and then they meet together at x equals 2 and y equals 4. So they actually do cross. But then once you get past 2, the blue one, the 2 to the x, well, actually x squared grows faster as you get past x equals 2, right? So it looks like x squared is gonna start growing faster, right? Because 2 to the x is kind of, it's starting higher, but it's taking its time going up, right? So actually it looks like x squared is growing faster when you look from 0 to 3. Okay. But when you go from 0 to 6 on x and we go up to 25 on y, you see what's happening? Like, it looks like, again, our f of x is 2 to the x, is the red one, and then our g of x equals x squared is the blue one. But then the red one starts growing faster again, okay? And then it overtakes the blue one. So yeah, it looks like the blue one's going faster at first, and it seems to be for a while, but then eventually the red one takes over and starts going really fast, okay? That's the 2 to the x is the red. And then finally, if we go from 0 to 20 on x and 0 to 1,000 on y, you see what happens. We don't see that activity down here anymore, but you can see that how much faster that 2 to the x is once you get way out on x, past 5, 10, 15, 20, right? That it grows much faster, and there's a huge difference there as x gets big. Okay? So 2 to the x is by far higher than x squared once you get to larger values of x. Okay, let's look at an application of an exponential function. First one we'll look at is compound interest. Okay, so with compound interest, that's basically how interest is calculated by banks. Is that simple interest is we give you a check for your interest and you keep the same balance. Well, compound interest is your interest gets put back in your account, so you earn interest on a higher balance next time. Okay, so your money. Your interest is reinvested. Okay, so we start with our amount of money, and we'll call it P for principal. Call it principal. Okay, and we'll invest that at an interest rate I per time period. Okay, and then after one time period, the interest rate is P times I. Okay, so that's simple interest, right? So think of it this as your the amount of money in the account is called A. Okay, then we have this relationship. A equals P plus PI, or P times 1 plus I. Okay, now what are those parts? The P is just what you initially invested, and then the PI is your interest that you earn. So you add the principal to the interest, okay? And then to get this, we just factor out the P. So P times 1 plus I, okay? Now, if we do that again, so if the interest is reinvested, okay, then the new principal, the new thing we're investing, is P times 1 plus I, because that's how much we have in the account now, okay? And then the amount after another time period is that new principal, which is P times 1 plus I, times another 1 plus I. Let's put a red there, okay? Okay. So what we're doing is we're taking our principal from last year, which is, you know, from the first year, P times 1 plus I, and then we're going to invest it again so we get another 1 times I, because we're going to take this thing times the I to get the interest, and we're going to take this thing times 1 to get the money back, right? So the money plus the interest, okay? So what we're doing is multiplying times 1 plus I twice, effectively, okay? So after 2 years, the amount in the account is P times 1 plus I squared, okay? Do you see the pattern there? So after 2 years, it's P times 1 plus I squared. After 1 year, it's P times 1 plus I to the 1. And then after a third year, third time period, the amount is P times 1 plus I to the third. Okay. So after K periods, or K years, the amount is P times 1 plus I to the K. Okay. Well, this is an exponential function with base 1 plus I. See, this is our base, okay, is 1 plus I to the K. Now that P is a multiplier. It's a little bit different. So that's not part of our base. That's just P times the exponential function. So what we're actually going to do is we're going to start with P. So our graph will look something like this. Okay. It's not, you know, it's an exponential function, so it grows like this. But we're not going to start at 1. We're going to start at P. Okay. So that's the idea there. Okay. Is that it starts at P instead of 1. Okay. That's what that multiplier P means. You're not going to start at 1. You're going to start at P. Because when K is 0, we have 1 plus I to the 0 is 1, and we just start with P. Okay. All right, so if the annual interest rate is R, and interest is compounded n times per year, okay, then in each time period, the interest rate, I, is R over n. And there are nt time periods in t years. So now we're going to look at what happens when you do it more than once per year, okay? That we're doing compounding maybe twice a year, so our n would be 2, or 4 times a year, so our n would be 4, or 12 times a year, so our n would be 12. So we're going to take our interest rate and divide it. So our interest rate will be R, and we'll divide it by how many times per year we do it. So if n is 2, we divide our interest rate by 2. And what we're going to do is do half the interest every 6 months, or 1/4 of the interest every 3 months, or 1/12 of the interest every month. So we're going to look at that periodic interest now. Okay, and this leads to our compound interest formula. Okay, what we're doing is we're taking the I and we're making it our interest rate divided by how many times per year. Okay, so if our R is 6 and we're doing it twice a year, this would be 3%, 0.03, right? So we divide by how many times per year, and then up here, instead of doing number of years, we're going to do number of periods. So we're going to take years times number of times per year. So now we're going to calculate interest every month if it's 12, or every 3 months if it's 4, if n is 4, or every 6 months if n is 2. Okay, so we're going to do it, more often. Okay, so that's how we do compound interest. Okay, so we can say compound interest is calculated by this formula. Okay, where A of t is the amount after t years, amount in the account. P is your principal. That's what you start with. R is your annual interest rate, or interest rate per year. N is how many times interest is compounded per year. And T is the number of years. Okay. So this is our formula for doing it n times per year. If we just wanted to do it once a year, it would look like this. Okay. So if we just do it annual, it will look like this. P, I forgot to do P, sorry. P times 1 plus R to the T. So this is annual. Okay. Now for annual, n is 1. Okay, we're doing it one time per year. So we can see how annual comes from this. But see, because when n is 1, this just becomes r, and when n is 1 here, it just becomes t. So this would be our annual, p times 1 plus r to the t, which is kind of how we developed our formula in the first place. When we do it more than once a year, we're going to have to do r over n and n times t here. Okay, so r over n here and n times t in our exponent. So we're going to calculate interest more often than once a year if n is more than 1. Okay, so let's look at an example. Let's say we invest $1,000 at an interest rate of 12% per year. Okay, and we want to find the amounts in the account after 3 years if interest is compounded annually. Now annually be n equals 1. Okay. Semi-annually be n equals 2 every 6 months. Quarterly would be n equals 4. That would be every 3 months. Monthly would be n equals 12. And daily would be n equals, now we use 365 here, right, because there's 365 days in a year. So this would be 365 times per year, okay, every day, right? So we're changing our n when we do this, okay? We're not going to do this calculation 365 times, we just use a formula, okay? So for annual, remember our r is 0.12, 12% as a decimal, okay? And then here our n is 1. T is 3 and n is 1. So 1 plus 1.012 to the third. So 1,000 times that is 1404.93 for annual. Okay. For semi-annual, our n is 2. So now we have a 2 here and a 2 here. Right. So 1 plus 0.12 divided by 2 to the 2 times 3 to the 6th power gives us 1418.52. Okay. Quarterly, our n is 4. So now we have 4 here and 4 here. And that gives us 1425.76. Monthly, our n is 12. Okay, so we have a 12 here and a 12 here, and that gives us 1430.77. And daily, our n is 365, right? So we put our 365 here and here, and it gives us 1433.24. Okay, notice, yes, you're earning more interest as you do it more often. And the reason is because you're putting interest in the account earlier. You know, here we're not putting interest in the account till the end of the year, right? Here we're putting it at the end of 6 months. Okay. Here we start putting it in after 3 months. Here we start putting in after, you know, the first month, the end of January, and here we're putting it in at the beginning of the end of the day, right? End of each day. So if you put interest in sooner, you're going to earn more interest, you know, overall, you know, because it's building up faster, right? Now we're putting smaller amounts right here than we are here, right? Because we're only putting a month of interest in there, or a day, in this case, a day of interest. But it still builds up more. But notice as we get closer and closer to daily, okay, it kind of levels off a little bit, right? I mean, it goes up, you know, here and here, and it goes up here. But as we get from monthly to daily, it only goes up a little bit more. So as we compound interest more and more often, it sort of levels off a little bit. Doesn't grow quite as much as you think it would. Right? I'll do another one of these in class, and we'll look at a different scenario where we do the same kind of thing. And then in section 4.2, we'll look at continuous interest, where we're constantly calculating that interest. Okay.